Good morning students. Today we are going to discuss about the state reduction techniques. First of all, I would like to tell you why do we need to reduce the states. So, a state table is given to you or a state transition diagram is given to you. Some of the states may lead to the same destination. So, they all become redundant. So, such redundant states will help us in reducing the circuit complexity by reducing the number of flip-flops and the gates what are required for designing this. So, we will have some redundant states and we have to eliminate them. So, to eliminate that, we have two techniques. One is called as the row elimination method, the other one is the implication table method. First, we will use the row elimination method and we will be reducing the number of states. Then we will go through the implication method. First, I will start with row elimination technique. So now, how does this row elimination method work? The first condition is, whenever I am seeing these are the states, this is my present state, on applying a particular input, A on 0, it will go to A on 1, it goes to B. So this becomes my next state and these are the output. And mind you, this is your Mealy model. Why it is the Mealy model? Because your output depends on the input, okay, and as well as the state. So this is a Mealy model. If it was a Moore model, I would have had a single column for my output because I have a single input and the output. So say output I have taken here as Z. Now what I have to do is I have to examine the rows which lead to the same state. But before I do that, I have to also check if the output is same. Only if the output is same, then from a present state, if it is going to the same next state from two states, then we can mark it as equivalent. Okay. Now, if I just see here, from A it is going to AB, from B it is going to CD, from C it is going to AD. Okay. Outputs are matching, but it is not going to the same state. Now, from D it is going to EF, output is 0, 1. From E it is going to AF, output is 0, 1. From F it is going to GF, output is 0, 1. From G it is going to AF. Okay. So now if you just examine this table here and here, that is state E and state G are leading to the same next state and their outputs also are same. So we can say that E is equivalent to G, and wherever I have the occurrence of G, I can replace with E. That is, both are equivalent states. You can retain any one. Usual practice, we retain the earlier state because G comes later, so I will retain E. So when I write this reduced table, how it looks? Present state, next state and the output. Okay. So I have A, B, C, D, E, F. I have eliminated G because E and G were the leading to the same state, so they became equivalent states. Okay. Now I told you that wherever I have the occurrence of G, I will replace with E. So here I will replace this with E. Anywhere I have G? No. Output remains the same. 0, 0, 0, 0. For C also 0, 0. Here 0, 1. E 0, 1 and F also 0, 1. So now again from this reduced table, I have to check if I have some other state which is equivalent. So if I examine these three, we have already examined, no one is equivalent. So now if I go through this, let me check whether it is equivalent. Now if you just check here, D and F are also equivalent because they are leading to the same state. Mind you, here you had replaced G with E. Because of that, this one more state we are able to reduce. So D and F are equivalent. So wherever I have the occurrence of F, I can replace with D. Okay. So I can replace with D. So wherever I have the occurrence, I will draw a new table only so that you don't get confused. D, E. So F I am eliminating here. Okay. So now AB, CD, AD, EF and AF, and outputs are 0, 0, 0, 0, 0, 0, 0, 1, 0, 1. Now I found that D and F are equivalent. So what I will do, wherever I have the occurrence of F, I will replace with D. I will replace with D. So it becomes ED and AD. Now again you check whether any state is equivalent. If you just examine, actually state C and state E also appear to be equivalent because they are leading to the same next state, but you have to be careful with the output. Output is not matching here, so they are not equivalent states. Okay, so now if you just see here, how many states we got? We got 5 states. How many we had? We had 7 states. So out of 7 states, we were able to reduce it to 5 states. So the number of flip-flops required for this, for 7 states and for 5 states, it remains 3 flip-flops, but however the circuitry, the number of gates required for this is less. Say for example, I was able to reduce to 4 states, then I would have ended up in only 2 flip-flops required for this design. But here, since I have 5 states, I require 3 flip-flops. But however, the circuitry would be reduced. So the same thing I will try to realize with the state diagram. This is your Murray model, mind you. I have A, B, C, D and E. So which are the equivalent states? I have written here. E and G are equivalent. D and F are equivalent. So we have eliminated G and F. Now A on 0, it is going to or stay in the same state, and output is also 0. Mind you, this is your Miller model. Input and output should be written beside each other. Now A on 1, it is going to B. Write this state diagram from the reduced table. Okay. Now output is 0. Now B on 0, it goes to C and the output is 0. B on 1 goes to D, output is 0. Now from state C on 0 goes to A and the output is 0. C on 1 goes to D and the output is 0. Now from D on 0 goes to E and the output is 0. D on 1, it's a self loop, okay, and output is 1. Then from E on 0 goes to A, E on 0 goes to A and the output is 0. E on 1 goes to D and the output is 1. So this is your reduced state transition diagram using our row elimination method. Hope this is clear to you. Next video we will check out how we can use implication table for the same example I will take and show you. Thank you.